Good morning, participants. Uh, Myself, Dr. Biplab Kumar Devnath. Today, I'm going to talk on deriving the expressions of forward and reverse reaction rates. This is the tutorial 4 on the fourth day of this GAN course on automotive emissions control and scopes of alternative green fuels. So let us move forward. So first question comes, what is reaction rate basically? Okay. So reaction rate is basically the decrease of the reactant concentration or rate of increase of product concentration. When we perform certain chemical reaction, we very well know that we first mix certain fuel and oxidizer together, okay, have a chemical reaction, okay. So while doing the chemical reaction, we can easily understand the quantity of reactants is going to reduce and the quantity of products are going to increase. So that is our main motive of chemical reaction. If you want to do a chemical reaction and if you want to have something out of it, then definitely the reaction should proceed towards the forward direction. So when it moves towards the forward direction, then the products, the quantity of the products or the concentration of the products should gradually increase and the concentration of the reactants should gradually decrease. Okay. So as far as the reaction rate is concerned, it is the rate of decrease of reactant concentration or the rate of increase of product concentration. Its unit is mole per meter cube second. So if we see a particular chemical reaction over here, that is E moles of capital E. Capital E is the element. How many moles E, small e? F moles of capital F. That is, F is also a species. It's also a constituent. It's a reactant. How many moles? F moles. They perform chemical reaction in between them and produce the products capital G and capital H having quantity small g and small h. Okay. So if it is the chemical reaction, then rate of increase of reactant concentration and rate of increase of product concentration, rate of decrease of reactant concentration, rate of product concentration is known as reaction rate. So the reaction is a bimolecular in nature, as you can see over here. So reaction rate of the participating species, okay, RR is given as minus 1 by E dCE dt, okay, is equal to minus 1 by F dCF dt should be is equal to 1 by G dCG dt should be is equal to, okay, this minus sign will not be there, 1 by H dCH dt. So here Cg and Ch are the constituents in the products. Their concentration should be increased. That means you see the rate of change of uh, concentration of G, the rate of the change of concentration of H per unit rate of time, okay, into 1 by the stoichiometric quantities, that gives you the reaction rate. So this is the reaction rate formula. If you notice that for the reactants we use a negative sign because the continuously the reactant constituents will go on decreasing, whereas for products, that means G and H, we don't use negative sign, that means a positive quantity, that means the gradually the product quantities should increase. Okay, so here Ce, Cf, Cg and Ch, these are called concentration of species, okay, moles per unit volume. So Ce, Cf, Cg, Ch, these are concentration of species. But from experimental observations, it is found that reaction rate of any species, say the species is I, okay, say you have a chemical reaction of C plus O2 is equal to CO2. So what is the reaction rate of C? What is the reaction rate of O2? Okay, so that is basically reaction rate for a particular species should be proportional to, this is called product sign. Okay, we have a summation sign like this, and this is called as product sign. So product of the concentration of participating species, so I is the species, and to the power gamma is basically the the stoichiometric quantities. Okay, so this is observed experimentally. So if there is a proportionate sign, then we can introduce a equal to sign in this particular equation, where we have to bring one constant that we will know. So this constant small k is called as the specific reaction rate of, or rate coefficient. Okay, so specific reaction rate or rate coefficient is very important, especially when you want to understand what are the conditions are occurring in a elemental reaction. Okay, elemental reaction, for an example, if I tell you, we know 2H2 plus O2 is equal to 2H2O. So that is a global reaction. Okay, so 2H2 plus O2 is equal to 2H2. When we write this type of equation, we call this a global reaction. Okay, but to perform this global reaction, there are many intermediate reactions occur. For example, hydrogen will break down to H, oxygen will break down to O. They may have a reaction of reacting with each other, and they form HO. Okay, or OH, whatever you tell. So this type of reaction which are occurring in between the this global reaction, these are called as elemental reaction. Okay, elemental elemental reaction. So for elemental reaction, is very important to find out the specific reaction rate or rate coefficient of every reaction. Okay, so that is done with the help of this particular formula, and this law, this is basically a law, and this law is called as law of mass action. Okay, so law of mass action always present when there is a chemical reaction between certain substances. Understood? Okay, so now let us try to understand what is happening in a first order reaction. Okay, so a first order reaction is a reaction, okay, where you see only one particular element is participating there with a forward reaction rate kf, and it is producing just one product. Okay, so reactant is one, product is one. Okay, so this type of reaction, why it is called first order reaction? Because you see in the earlier law of mass action, here you have the constituents, here concentration only one. Okay, only one constituent is there. So this type of reaction is called as first order reaction. Now in this first order reaction, if we want to see what is the reaction rate, then reaction rate of hydrogen, so the hydrogen is the reactant, reaction rate of hydrogen is equal to minus, you see it should be 1 by the stoichiometric concentration of hydrogen, but there is only one, that's why it's nothing is there, minus dCH2 by dt. Then using law of mass action, we can write that this should be equal to kf into CH2. Now here we have considered only the forward reaction rate kf, so that's why we have written kf CH2. Okay, it should be actually CH2 to the power the molar concentration of the reactant, but this is only one here, so that's why it is not written here. Now if we want to integrate this particular equation for a period, for a time period of 0 to t, then what we get? So let us do the integration between this time range of 0 to t. So when, let us consider when time is equal to 0, then the concentration CH2 is equal to basically CH2 naught. Okay, so initial concentration. But when time is equal to t, after a time t, the concentration of CH2 changes to CH2T. Okay, so between this limit, if we want to do the integration, so CH2 we bring it down at the denominator. Okay, and dt we take up here. Okay, and we do the integration. Now here we understand that Kf is a constant, so it will be outside the integral. Okay, so when you do the integration, then from this integration we find out that because it's within the limit, so ln ch naught ch to naught by ch to t. Why it is ch to naught is gone up? Because I have used the negative sign inside it. So when negative sign is there, it will just flip. So ln ch to naught divided by ch to t is equal to kft. Okay, so from here we can write ch to t. Okay, what is the concentration of hydrogen after a time t should be equal to ch2 naught. What is the initial concentration into exponential of minus kft. So in that way we can find out what is the uh, concentration of hydrogen. So here you see hydrogen concentration decreases exponentially with time. Okay, all unimolecular reactions follow the first order kinetics. So if you want to plot what is the variation of the CH2, okay, CH2, okay, concentration of hydrogen over time, then you will see that it will follow a exponential route. Okay, so this particular condition with a different constant rate means kf may vary, but this particular route will definitely follow. This means all unimolecular reactions follow the first order kinetics. Understood? So now let us move to the second order reaction. Okay, so let us consider a second order reaction where you have E and F as the reactants, E and F as the reactants. Okay, and they are producing the products G and H with a forward reaction rate Kf. Okay, so most chemical reactions are bimolecular in nature. We tell the certain reaction has certain amount of fuel, certain amount of oxidizer. Especially if you talk about IC engine combustion is concerned, then definitely there will be a certain fuel and there will be oxygen as the oxidizer. So definitely there will be minimum two substances in the reactants. So whenever there are minimum two number of substances are there in the reactants, this is called bimolecular in nature. Okay. Now this bimolecular nature, because of the presence of multiple molecules, the reaction rate equation becomes a second order reaction rate. Okay. So let us try to see. Then the concentration of E and F at any time, we can write that Ce is equal to Ce is equal to Ce naught minus Cx. Okay, Ce naught minus Cx. Here Ce naught is the initial concentration. Okay, and Cf naught is the initial concentration again for the constituent F. Okay, and Cx is the, here you see C naught and Cf naught are the initial concentration of the species E and F, and Cx is a portion of species E and F concentration that is consumed during the reaction. Okay, so here this Cx concentration, we are assuming that the concentration of Ce, okay, is equal to the concentration of Cf, which is actually participating in the chemical reaction from the initial constituents. Initial concentrations are Ce naught and Cf naught. From there, Cx quantity of each of the substances are taking part in the chemical reaction. So this is considered equal quantity for each of the cases. So if it is the case, then the reaction rate equation we can write as dCx, okay, dCx dt, change of Cx concentration should be equal to Kf C naught minus Cx into Cf naught minus Cx. Okay. So if we now integrate, in order to integrate that, what we do, we bring this particular constituent, this particular concentration, we bring it down here. Okay. And dt we take up. Okay, so when you do this, so the C naught minus Cx, Cf naught minus Cx comes down, and Cf naught minus Ce naught we multiply in both the sides. Okay, why we multiply? Because then we can break it into two components. Okay, so here you see dCx divided by dC naught minus Cx minus dCx divided by Cf naught minus Cx, because if you do the subtraction from here, so it will be Cf naught minus Cx minus C naught plus Cx. Cx cancels out, so you have Cf naught minus C naught. Okay, this is equal to Kf into this quantity. So now we integrate this. So after integration, we get it. We get like this. You see, Cf naught ln will come up, ln into Cf naught minus Cx. Okay, and here will be ln of C naught minus Cx. But in both the cases, Cx is the variable, but Cx is having negative sign before. So a negative sign will also be added there. So it will become plus and it will become minus. So that's the reason why you see ln Cf naught minus Cx divided by C naught minus Cx is mentioned here. Should be equal to Kf into Cf naught minus C naught into T plus constant. Now, for this, if we consider time t is equal to 0, Cx is equal to 0. Okay. Initial, when you start the reaction, then there is no constituent participant in the reaction, right? So at t is equal to Cx is equal to 0. So in this particular equation, you see this Cx and this Cx will be equal to 0 at time t is equal to 0. So constant is equal to ln Cf naught by C naught. So you see constant is equal to ln Cf naught minus C naught. Now when we put this in this particular equation, so we get ln Cf naught minus Cx divided by C naught minus Cx should be is equal to Kf into Cf naught minus C naught into T plus ln of Cf naught by C naught. Okay. So from there, if we write Kf is equal to, you see this particular this entire part will go down. So Cf naught minus C naught. Okay. Into ln of Cf naught, uh, ln of Cf naught into C naught minus Cx divided by C naught into Cf naught minus Cx. Okay, so this is the forward reaction rate equation. Now, if I tell you, can you do a homework, small homework? Can you derive this forward reaction rate equation for a second order reaction having Ce is equal to Cf? Okay. So if Ce, that means the constituent, the concentration of E, if it is equal to concentration of F, then how this reaction will change. So try this at your home. Okay. If you practice, you will understand clearly. Okay. Now, reverse or backward reaction. I was telling in the last class that when a chemical reaction occur, it is not mandatory that all the times it will proceed towards the forward direction. That means if say E constituents is reacting and giving you F constituent, it is not mandatory that F is again not forming, giving back to E, coming back to E. Okay. So that means what? Along with forward, there is always a chance of a backward reaction. Okay, so most chemical reaction which are in biomolecular nature, they are primarily occur in the second order. Okay, but at time t is equal to 0, if we consider like this, that the concentration of E is Ce naught, okay, and concentration F is 0, but at time t concentration of E should be Ce, okay, and the concentration of F should be, acha, here at time t is equal to t, the concentration of E changes to C, whereas a concentration of F the comes to Cf. Okay, so this is continuously changing. So here, from here, the forward reaction rate is Kf into C. Okay, and the backward reaction should be Kb into C naught minus C. Okay, because in the during the backward reaction, okay, during the backward reaction, what about the formation of C is there? Okay, that quantity is again participating in the reverse. Okay. So initially C naught is the quantity. After time t, C is the quantity. That means C naught changes to C. Okay. Then what is the remaining portion? Okay. So the remaining portion is again participating in the reverse reaction. So net rate of consumption of E should be equal to minus dCE dt should be is equal to Kf into Ce minus Kb into C naught minus C. That means in the forward reaction, what are the constituents are forming, minus in the backward reaction, what are the constituents are participating. So after a certain time, the reaction will reach equilibrium. The concentration of E at that constant instant, let us consider this CE equilibrium, and at that time dCE dt should be is equal to 0. So if dCE dt is equal to 0, then we can rearrange this particular equation in this particular form. Okay, this equation, let us consider 1. So 1 implies 2. Okay, 1 changes to K, C becomes C equilibrium. So equilibrium, Kf C equilibrium minus Kb into C naught minus C equilibrium. So from here we get the backward reaction rate and forward reaction rate relation. So backward reaction rate should be is equal to Kf into C equilibrium divided by C naught minus C equilibrium. So this, from this equation we will find out separately what is the forward reaction rate and what is the backward reaction rate equations. Okay. So now minus dC dt. Okay. So what we do, we put this particular equation, the we put the uh, quantity of Kb, okay, this quantity in this particular equation 1, and we try to find out the forward reaction rate. Okay, so after putting this value, we get minus dC dt should be equal to Kfc minus C naught minus C into Kf C equilibrium divided by C naught minus C equilibrium. Okay, so let us bring down the C part. So from here, okay, uh, we do the multiplication. Okay, so from here if we do the multiplication, so here you see, from here if we do the multiplication, then what happens, we have kf into ce, okay, into c naught, right, c naught minus kf into ce into ce equilibrium, okay, minus kf into c naught C naught into CE equilibrium plus this minus minus plus KF into CE into CE equilibrium. Okay. So what we can cut over here, C naught we can cancel, right? No, we can cut minus KF C equilibrium minus KF C equilibrium. So finally from here we can take KF outside the bracket, and we can take out C naught. We can take C naught outside the bracket, C naught outside the bracket. Okay, so we have CE minus C equilibrium divided by C naught minus C equilibrium. Okay, so now we can easily do the integration. Okay, so dC divided by C minus C equilibrium should be equal to minus Kf into C dot integral of dt by C naught minus C equilibrium. So if we do the integration, we find that ln C minus C equilibrium should be equal to minus Kf T C naught divided by C naught minus C equilibrium plus constant. Okay. Now, if we use the boundary condition at time t is equal to 0, C is equal to C0. Okay. Then with this we can find out ln C naught minus C equilibrium is equal to constant, because time t is equal to 0. If we put this term will become 0. Okay, so from here we get ln C minus C equilibrium divided by C naught. After putting this value in the form of constant, this will come down below. So C naught minus C equilibrium should be is equal to minus Kf T C naught divided by C naught minus C equilibrium. Okay, so from there here we can find out what is the forward reaction rate. So the forward reaction rate Kf is equal to, here you see Ce equilibrium minus Ce naught. Okay, minus is actually taken care of, divided by T into C naught into ln Ce minus Ce equilibrium divided by C naught minus C equilibrium. So this is basically a forward reaction rate for an bimolecular reaction. Okay, so forward reaction rate of a bimolecular reaction. So now putting this value of Kf in this forward and backward reaction rate, here you see in this particular reaction, right hand side reaction, we'll put the value of Kf and we find out what is the backward reaction rate. Okay, so the backward reaction rate Kb is equal to minus Ce equilibrium divided by Tc naught ln Ce minus C equilibrium divided by C naught minus Ce equilibrium. So that is basically the backward reaction rate. Okay, so it is very, very important to find out the backward reaction rate for any type of reaction. Here we have tried to solve and explain you how we can calculate the backward reaction rate. Is it understood? Anyone doubt? Any query? So if no query, let us try to solve a problem. Okay, so it is told that in this problem, in a first order reaction, oxygen O2 breaks down to 2O. It is observed that 40% of O2 dissociates, okay, in 100 seconds. 40% of oxygen breaks down into 100 seconds. Determine the specific reaction rate coefficient and what is the half-life of the reaction. Okay, half-life means what? When the 50% of the oxygen will break down. Okay, so let us write the chemical reaction first. So the chemical reaction is oxygen breaks down to 2O. Okay, so we can write the equation of reaction rate dCO2 divided by dt should be is equal to minus of K, let us write is a forward reaction rate, into CO2. CO2. Okay, so we uh, we found that the time is changing from t is changing from 0 second to 100 second. Okay, so if it is the case, then CO2 means what is the concentration of oxygen after 100 seconds. So initially the concentration now, so CO2, the concentration of oxygen, okay, initially whatever is there, but after 100 seconds the 40% of the oxygen has been dissolved. So how much is remaining? Remaining is 100 minus 40. So that is basically 60 units of oxygen is still remaining. Okay, so if it is the case, then we can write this particular equation. We can do the integration. If you want to do the integration, we can also do that one. So integration dCO2 divided by CO2 should be is equal to minus Kf into integration of dt. Okay, so From there, if we do the integration, we can write ln, okay, CO2. Acha, what is the limit? Time is 0 to t. Okay. And what is the concentration? Initially, it is started at 100, but it is finished at 60. Okay. So, or for the timing, let us write only with the nomenclatures. Then it will be easier to understand. Okay. So, let us write this is CO2 0 to CO2 T. T. Okay. So CO2 T divided by CO2 0, okay, should be is equal to minus Kf into T. Okay. So from here we can now put the values after time t. This is 60. So ln 60 divided by 100 should be is equal to minus kf into 100. Okay. So from here we get kf. You will supposed to get after doing the equation 100 will go down, minus minus will cancel out with the ln, and you will get f is equal to 5.1 into 10 to the power minus 3 per second. Okay, because here you see this 60 will cancel out whatever may be the concentration. Here you have 100 seconds, so 100 will go down. Okay, so 100 second will go down. So it will be kf, this 5.1 into 10 to the power minus 3 per second. So this is the reaction rate uh, of this first 100 seconds. Okay. Now what is the half life? Half life of the reaction. Okay. So half life of the reaction, you will see the same equation will follow. Okay. So the half life of the chemical reaction, half life of the chemical reaction. Okay. So here you see we'll put you see we can directly use this equation kf, okay, minus kft should be is equal to ln CO2 T divided by CO2 0, right? So half life means what? What do we want to find out? We want to find out the time. So from this equation, time is equal to 1 by kf into ln. We can write CO2 0 and CO2 50%, right? 50%, or okay, better light uh, for clarity. Okay, let us say half life. Okay, age. Okay, so from here, 1 by kf is how much? 5.1 into 10 to the power minus 3, right? Into ln of how much is CO2 0? CO2 0 is 100, and at half life, the concentration should come down to 50, right? So from here, if you do the calculation, you are supposed to get the time should be 135.9 seconds. Okay, so this is the half life of this equation. Any query, participants?
No, sir.
Okay, so this is first problem. Let us go to the second problem. So in second problem, what it is told? It is told that hydrogen iodide with initial concentration of 73 mole per meter cube is decomposed to produce H2 and I2 molecules. As per the following reaction, 2HI should break down to H2 plus I2. It is found that 20% of initial hydrogen iodide is decomposed in 45 seconds. What is the half-life of this reaction? If the initial concentration of hydrogen iodide is doubled, what will be its half-life? So let us write the equation. The equation is 2Hi should be is equal to H2 plus I2. Okay. So reaction rate of Hi should be is equal to dCHI divided by dt should be is equal to minus of Kf into. Now here you see you have 2 moles of hydrogen iodide, right? So as per law of mass action, concentration of hydrogen iodide should be power of 2. Okay. Why? Because as per law of mass action, this is basically reaction rate of I should be is equal to product of I is equal to 1 to N. Okay. C of I gamma I. What is gamma I? This gamma I basically is the stoichiometric constituent, stoichiometric quantity. Okay. So, so let us consider that initially when time is equal to 0, then CHI is equal to CHI naught. Okay. And time T, okay, C, the quantity becomes CHI becomes CHI T. Okay. So if it is the case, then let us do the integration. So how we'll do the integration? We'll bring this dCHI divided by CHI square should be is equal to minus Kf into integration of dt. Okay, integration of dt. So here time 0 to t, and here initial concentration CHI naught to CHI T. Okay. So if we do the integration, here you see this is a power. So integration of dx by x square, what happens? Anybody knows? This will be half of, right? Is it half? Hmm? Not half. This is actually minus 2 plus 1, right? So minus actually comes at the front. Okay. So this is what minus of 1 by CHIT, okay, minus of CHI naught. Am I right? Okay. This should be is equal to minus of KFT. Minus minus cancels out. Okay. So KF is equal to KF is equal to 1 by T within bracket 1 by CHI T minus of CHI naught. Okay. So if this is the case, then from here, what is told that hydrogen iodide with initial concentration of 73 mole is decomposed to produce H2O2 molecules as per the following reaction, it is found that 20% of the initial hydrogen iodide is decomposed into 45 seconds. So 1 by 45 second, okay, and 20% is decomposed, right? So this will be, what is the remaining quantity after time t? So that will be 0.8 into how much? 73. 73 minus 1 by 73 moles. Okay. So if it is the case, then we find out. Now here you see the moles per meter cube already given. Okay. So if it reverses, okay, moles per meter cube is reverses, then it will be the quantity you are supposed to get 7.61 into 10 to the power minus 5 meter cube per mole, right? It will be just reverse and per second. Okay. So this is the forward reaction rate for the hydrogen iodide, breaking down to hydrogen and iodine. Okay. So what we have found out, what is the reaction rate, then what is the half life of the reaction? So half life of the reaction, same way, just in this case it will be 0.5 of 73. So the for half life calculation, k, we need time we need to find out. So time is equal to 1 by kf into 1 by 0. Half life, so let us write t 50%. So 0.5 into 73 minus 1 by 73. Okay. So from here, kf will put this value will put here. So we will get, it is around 180 second. Okay. You are supposed to get 180 second as the half life of the reaction. Okay. Now it is told, if the initial concentration of hydrogen iodide is doubled, what will be its half life? Okay. What will be its half life? Okay. So the, if even if the concentration is doubled, the reaction rate is not going to change. Okay. So the reaction rate will be remaining same. So for 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 double initial concentration, the half life, okay, so t say dash 50%, 50% is equal to 1 by kf, okay, within bracket 1 by 0.5 into double the initial concentration, right? So 73 into 2 minus again 73 into 2. Okay. So use the same kf value over here. So when you use the same kf value, you are supposed to get that time is 90 seconds.
Sir,
Yeah.
sir, will KF not change, sir? KF will also change, no, sir?
No, kf change does not depend on the concentration. Kf only depends upon the temperature and the pressure of the system. Okay, temperature, pressure of the system. What is the properties of the system? The presence of concentration does not affect the reaction rate. Okay.
Sir, but if it is given in the start only different concentration, then KF would have come differently.
Which one?
Sir, if directly in the starting, if they gave 73 into 2, like different concentration in the question, then we
Huh.
would get KF differently, no, sir?
then time will also change, no?
Okay, okay, okay.
Okay, for the reaction, for a particular reaction, okay, for the fixed type of constituents, the reaction rate remains same. Okay, but if uh, the quantity, the material changes, then the reaction rate changes. Okay, because reaction rate depends upon how quickly the bonds are breaking and how quickly the bonds are forming.
Okay.
Okay, any more query? Any doubt? Okay, so if there is no query, there is a homework problem over here. Can you derive equation between reaction rates and equilibrium constant? Okay, so this is a homework for you. I have discussed in the last class about the equilibrium constants. Okay, but reaction rates, what we have discussed today, these are basically for the elementary reaction, what is the specific reaction rate or rate coefficient. So can you find out a relation or multiple relations between the reaction rates, either it is a forward reaction rate or reverse reaction rate, and equilibrium constants. Okay, now equilibrium constants, for your understanding also, again I am telling, equilibrium constants can also be two types. One maybe for molar basis and one if it is for the mass basis way. Okay, so this is a homework for you. Try to find out the answer. Okay, any query, anything you have not understood or want me to discuss again? Okay then. Thank you for joining this session.